Speaker is Mark Sonter. He directs the Deep Space Group, developing technologies and operational concepts needed to harvest commercial quantities of asteroid resources. He's an independent scientific consultant in the Australian mining and metallurgical industries with specific major expertise in radiation management and uranium, mineral sands, rare earth exploitation, mining and processing. Over to you, Mark.
There we go. This thing working? Hello? Yes?
Yeah.
I'm giving this talk on behalf of Daniel Faber, our CEO, who can't be here. He's off chasing investors at the moment. And how do I work this thing? Oh, that's not the way. All right. After yesterday afternoon's various discussions about worrying about the ethics of mining in space, and particularly after Phil Metzger's impassioned plea for injecting political pressure into the system to make humanity's movement into space a reality, I thought I would insert this slide, should we want to mine asteroids. And we're mining asteroids not primarily because we want to make money. We're mining asteroids because we want to help get humanity into space. We want to address the limits to growth paradigm that Phil Metzger talked about. We want to give a way forward in his discussion of the breakout into space or descent into barbarism dilemma. We want to address the single planet catastrophe situation by making us a multi-planet species, and we want to bear in mind the Fermi's paradox situation that SETI's been looking for intelligent life in outer space for 30 years and has not found anything. If we are indeed all there is, then we damn well better get out into space. So Deep Space Industries seeks to facilitate and enable that breakout. We need the video, don't we? So I thought I would entertain everybody with the video that we played when we made our first public announcement of our presence. If we can get this.
Why shouldn't the future be better than today? But where will it come from? Simple. What will tomorrow look like? Our world is at its limits, and yet we all want more. And why not? Why shouldn't the future be better than today? But where will it come from? Simple. Our tiny planet sits in a vast sea of resources, including millions of asteroids, bathed in the sun's free energy 24 hours a day. The same rocks that could fall from our skies also contain everything we could ever need, both out there and down here. It's time someone seized the opportunity. Deep Space Industries. Deep Space is a new kind of company with a new kind of plan. We don't build rockets. We don't do astronomy. We are explorers and harvesters, makers and suppliers. As they say, timing is everything. And for space, right now is the time. In fact, some of the planet's most successful people are placing their bets on this new frontier. Meanwhile, NASA and others are planning new missions to the Moon and Mars, with new space facilities in free space joining the billions of dollars worth of communication satellites already in orbit. And as they reach beyond Earth's orbit, Deep Space Industries will be there with the fuel, air, and materials they will need to succeed and grow. DSI has assembled an international team of well-known experts and young innovators who are building on our space legacy and creating new technologies and approaches to open the frontier. We will develop and prove ourselves in 3 areas: exploring and prospecting for asteroids, harvesting and returning asteroid materials, and processing those materials for use in space and on Earth. early systems will be small and largely off-the-shelf components re-engineered for deep space. We will hitch rides on much larger missions with multiple ways to get into space, where our job really begins. With mission costs so low, we'll be able to attract commercial sponsors and build fleets of vehicles to assure our success. Early markets will be satellites in need of fuel, government outposts and commercial facilities, and missions between the Earth and the Moon. As we gain expertise and develop our systems, we will grow them as the frontier grows, so that when the time comes, DSI will be ready. We will be the gas station, the oasis for air and water, and the building supply center for the frontier. This is a long game, perhaps the longest ever. While we earn our way, the long goal is to create a better future for all of us through space resources. When the first asteroid is mined, deep space will be there. When the first space power plants come online, deep space will be there. When the first space colonies are built, deep space will be there. We can have it all. We can have an amazing future. The resources of space will lead to a new renaissance, both in space and back here on our precious Mother Earth. We are deep space. The frontier is coming, and our time is now.
So there's the vision. Excuse the sepulchral tones and everything. We've got a team. We've assembled about 15 people so far in our team, and that's just some of us. Importantly, we've got John Lewis on board, who's an encyclopedic source of information on asteroids, meteorites, and 30 years of thinking about how to process asteroids. Mark Raymond is still the chief engineer of the Dawn mission, and before that the Deep Space One mission. Daniel Faber, of course, is an alumnus of UNSW. The task is to have money coming in the door so that we can grow and do the things we need to do, and that has set us on the path of having two major prongs to our activities. One is the technology development, the here and now, the seeking contracts to design things and build things, and the other is the strategic long-term task of figuring out how to go for and get and process deep space resources, asteroidal resources. So materials on orbit is the long-term plan. We want to be able to provide fuels, consumables, metals for construction, and so on. And the how we're going to get there is the here and now business of building Cubesat type spacecraft. When you see a rocket launch like that, it looks very impressive, but to those of us that are interested in space, it represents the serious constraints that presently exist. The constraints in terms of launch cost, $10,000 per kilogram to low Earth orbit, $30,000 per kilogram to geostationary orbit. The size constraints of the payload bay, the fairing shroud. Everything has to be able to be folded up to fit inside this fairing shroud. So there's a limit to, there's a cost demand. There's a limit to the size of that which can be launched. There's a limit to the mass which can be launched, and there's the extremely demanding launch environment in terms of vibration and acoustics. So a picture like that is a picture of our present constraints rather than of our present capabilities. And the way around those constraints, of course, is to source your material in space. Propulsion technologies that can be refueled on orbit are an important future market. Brains manufactured on Earth and brawn manufactured in space. Near-term technology drives future markets for resources. I want to flip through this because it's not really my presentation, it's Daniel's, and I'll make comment where it occurs to me. So we focused on asteroid-derived products being water and other volatiles for the purposes you see there, and extraction of metals for the purposes that you see there. We've had significant recent feedback from geostationary communications satellite operators that they really would like to be able to build large, indefinitely large, in-space antennas and solar PV panels to overcome the sorts of constraints I talked about a couple of slides back. So don't launch, harvest. We wish to span the entire mining ecosystem from identification of target types through to identification of specific targets all the way through to refined products, rather than merely focusing, for example, on prospecting. And you can map it across from terrestrial mining industry to what we need to try and do. I'll be talking more about the mapping across from terrestrial geoscience industries, mining and processing later on this afternoon. Much the same in that slide. We are working up designs for what we call Prospector, a small Cubesat type 6U to 12U size probe to go out and rendezvous with targets, an extractor to a small probe to bring back samples for test work, and then finally the full-scale harvester, the intent of the harvester being to bring back 500 tonne to 1,000 tonne payloads to a high Earth orbit where further processing can occur. Short-term products and services map against that in terms of designing and building agile nanosats, pursuing robotics and propulsion, and I'm the one that is seeking to lead the building of developing the deep space mining concepts and how we do these things. So I should mention a couple of our near-term products, one being the Agile Nanosat platform that we're proposing to academia and space agency people and commercial interests around the world. And the other being the mothership, which we're proposing to agencies and institutions around the world that wish to have a cheap way of accessing asteroid science. We've actually got a number of letters of intent for slots on the mothership already in play, and we're seeking more, of course. So our mining spacecraft, as I said, are the prospector, the extractor and the harvester, and those are their tasks. The prospector program is a low-cost initial asteroid characterization mission, or missions, set of missions. It's called a prospector, but we believe we'll be going out to targets that are already characterized to the extent where we can set a probability on being able to extract water. A probability that's high enough to say it's a good risk. The prospector missions, therefore, are really to be thought of as technology risk reduction missions, geotechnical missions, missions to test the cohesiveness and the diggability of the regolith on the target bodies, so that we begin to get an idea of real ground truth for how you design such things as anchoring and mining equipment. They're specifically aimed to be the smallest, simplest, cheapest spacecraft possible to accomplish meaningful resource assessments. They're intended primarily for rendezvous. We are tending to walk away from the flyby missions as being, one shot and you've lost your chance. If you can't find the thing on the way out and you fly past it, it's a lost mission. Whereas if you intend from the beginning to rendezvous, then you can do lots of imaging of the object. You can get its mass by looking at its gravity, whereas you can't necessarily do that in a flyby. The design philosophy of the prospector is a microspace approach, aggressive minimalisation or minimalism, no death modes, no exotic technology, using off-the-shelf or proven or very near-term technologies, and multi-payload capacity. We're presently going through the the thought process of trying to identify what the baseline instrumentation payloads should be, and we can have conversations with people who want to make suggestions to us. There's the prospector plan platform overview. Can you read it? Mission life 1 year minimum, 30 days minimum at asteroid, spacecraft mass 34 kilograms wet, 21 kilograms dry, launch mass 191 kilograms, delta V 4 kilometres injection, nominally from a 200 kilometre low Earth orbit. The rest of it is beginning to get out of my area of comfort, my comfort zone. The concept of operations is that the prospect and injection stage are launched to LEO, commissioned in LEO, then injected into the trajectory to the near Earth asteroid. Then we have the rendezvous and proximity operations, and there is an alternative of a flyby tour of multiple asteroids, but as I say, that's going on the back burner at the moment. Trajectory analysis. If you go into something like NASA's trajectory browser and you put in sensible search terms, you find an amazingly large number of mission possibilities jump out at you. Now, the problem that we all have is that we know the spectral information, we know the albedo information about a very, very, very tiny proportion of those objects that become available to you theoretically when you look at something like NHATS or something like trajectory browser. But there are something like 13,000 near-Earth asteroids. Of those 13,000 near-Earth asteroids, something like 7,000 of them are energetically, intermittently closer than the Moon. In other words, a lower delta V to get to them than to land on the Moon. Intermittently. And an unknown number of them are in fact, of those ones, are in fact good resource targets. But if you look at the statistics, and I'll go through this more this afternoon, you look at the statistics of the proportion of C-type asteroids versus S-type asteroids, and if you look at the likely water contents of those C-type asteroids, you get a surprisingly high probability of successful water extraction, and even higher if you can sieve down by zeroing in on the low albedo targets. So there's lots of targets potentially available to look at. Scott Dorrington spoke about several of the targets yesterday. You'll remember 2014 EK24 being a classic, but he mentioned a number of them. Clearly his thought processes are similar to ours. What goes into our target selection, well, that's a secret, obviously, but there's plenty of potentials. So that's really where I got to. That's what we're on about. I've got a couple more backup slides, but how's the time going?
Stop there is good.
Stop there is good?
Yeah.
Good.
We have time for questions.
I'm wondering what Deep Space's vision is for communicating with the people of Earth about how space will benefit the people of Earth, so that the people of Earth will be on side. In my communications with my many articles in local media, I get a lot of feedback about how people are a bit angry with the space industry that it is out there, but what's it going to do for us, and we should get our act together on Earth before we do anything out there. It's quite a grumble, and I'm wondering, it's a PR exercise, and it has to be a demonstration to the people of Earth that space is relevant.
I was really struck by Phil Metzger's presentation yesterday afternoon, and what I could do is replay that in my mind to you.
And to some extent, that might be a better question for the panel rather than for an individual speaker.
I understand, and how do we continue to present what our vision is? Well, that's the reason I showed that somewhat American video. I think all we can do is say that there's a pessimistic view of the future, and here we are presenting an alternative, optimistic view of the future. Have a look at it.
Yeah.
I was just concerned about TTC. You're going to need about a 70-metre ground dish to do that with this mission. Are you planning to build that yourself, or do you think the Deep Space Network will give you adequate time?
I've not been pursuing that question. That's one that Daniel would be better to answer, but we're certainly not going to build our own dish. We've looked at radio versus optical. The nominal is still radio, but I don't know details of what we're thinking, where I think he's up to.
Leslie?
When do you anticipate the research missions with the Cubesats to first begin launching?
Leslie, I purposely took the dates off those slides. We used to say 2017. And everything depends. Everything depends on success in raising money. And we've had some recent, our first genuine recent success in raising serious money, rather than just sweat equity and friends and family stuff, was about a month ago. And we're working on a $3 million seed fund round to close by the end of the year, which we are now reasonably confident in, to go into a $50 million or thereabouts around sometime mid next year or later. Everything depends on success in raising money.
That's a generic statement. Okay, can we just leave that for the moment, and we'll probably return to some of these issues during the panel. Thanks, Mark. The next speaker is Andrew Bartlett.